In this video, we're going to explore calculating the probability of dependent events. So let's begin by defining what that means. It means that we have two events. We'll call them A and B, so instead of 1 and 2, so we don't confuse them numerically. And they have an overlap between them, meaning that event B can't happen unless event A does. So the probability of event B happening after event A does is equal to the probability of where they overlap divided by the probability of the first event happening. Rearranging this equation can also yield it in this form, where the probability of them overlapping is equal to the probability of the first event times the probability of B as it depends on A. Seems a little wordy. Let's get to some examples that exemplify how this works. So in example 1, we have a pair of fair dice being tossed. So we know that when we have a pair of fair dice being tossed, that there are 36 possible outcomes. We've explored this before in previous lessons. So if the sum of the two die is a value of 6, what's the probability that one of the dice is a 2? Let's let event A be having a sum of 6, and let's let event B be having a 2 on one of the die, or one of the dice. So I'm going to show visually a couple of ways of representing this scenario. I can show event A and event B like this, where event A is the sum of 6 and event B is 2 on a die. And then we have the overlap region here where you have the sum of them being 6 and there being a 2 on a die. So what I'm going to do is I'm going to color code these so that we can see sort of each scenario. So a sum of 6 would be anything that is to the top left corner of this that would be this diagonal value right here. So I'm just going to do them as circles like this. Okay, there's our sum of 6. In order to have a 2 on a die, we would have anything that could be in this row here. I'll show it with green X's. And also it could be anything that's in this row here. Okay, there's our 2 on a die. Now we have some places where those two events overlap. And you can see that there are two such scenarios. This one right here and this one right here. Okay, so to find out what the probability is that one of the die is a 2, we're calling it event B. It's dependent on there being a sum of 6. So that's going to be equal to the probability of where these two overlap. I'm going to put here sum of 6, or sorry, 2 on a, yeah, we'll do sum of 6 intersecting with 2 on a die, divided by the probability of the first event, which is having a sum of 6. Okay? So, what is the probability of these two where they overlap? Well, there are two scenarios where they overlap out of a total of 36 possible scenarios. Underneath, the number of events where there's a sum of 6, or the orange ones, has a value of 5 out of 36. Now, I want to just do a little sidebar here. This looks a little funny, but it can be thought of as being 2 out of 36 divided by 5 out of 36. And we know that one way that we can solve division of fractions is to invert and multiply. So this becomes 2 out of 36 times 36 over 5. There's a factor of 36 in the top and the bottom of both of those factors, which means the probability for that second event is equal to 2/5. Okay, let's try some more examples. I'm going to leave the top part on so that we can refer to it. So in example 2, we have 2 cards being selected from a deck. And what is the probability that both of them will be spades? So we're going to let event A be drawing the first spade. And we'll let event B be drawing the second spade from the deck. We can draw this as a Venn diagram as well, where we're letting draw number 1 be getting the first spade and draw number 2 being the second spade. And we're solving for this overlap area in here. So we can start to set this up. We can say the probability where the first spade and the second spade are both drawn, one after the other, is equal to, and I'm going to use this version of the equation this time, probability of the first event times the probability of the second event after the first event has happened. So, what is the probability of drawing a spade? Well, we know that there are 52 cards in the deck, and of the 52, 13 of them are spades. So there's a 13 and 50 out of 52 probability that a spade will be drawn. However, once that card has been drawn, it is not put back in the pile. So if I want to draw the second spade, I'm now drawing it from a deck of 51 cards instead of 52. Also, one of the spades has been taken, so now there are only 12 that can possibly be chosen for the second draw. All right, to solve this, I can do multiplication across numerators and denominators. I can also try to reduce it ahead of time. I know that there's a factor of 4 that can go into both of these, and so I'm going to take out that factor of 4. Okay. Similarly, actually, I'm going to go back just because I'm doing this a little differently and I'm trying to do it in my head and I'm not succeeding well. Let's do it the long way instead. Let's go back to our 13 out of 52 for the first one and our 12 out of 51 for the second one. I'm going to reduce these fractions before I multiply them to make the math easier. I know that 13 out of 52 can be thought of as 1 out of 4. There we go. And 12 out of 51, they're both divisible by 3, so this can become 4 out of 17. There we go. I'm going to do the reductions of the factors here before I do the multiplication, and that's cool. Then I notice that there's a factor of 4 in the numerator and the denominator, which leaves me a probability of 1 out of 17 for that overlapped area. Okay, let's do a couple more examples for dependent events. In example 3 of your notes, we're going back to a pair of die being rolled, and we're going to look at 2 sub-scenarios. So this time the probability of rolling a sum less than 6 and 2, given that one of the dies is a 2. So again, let's set up our little table of sums for rolling 2 die. There we go. And let's begin this part by defining our 2 events. So we're going to let event A be that one of the die has to be a 2, or one of the dice. And we'll let event B be less than a sum of 6, or a sum less than 6. There we go. All right, so what we're doing here is, again, if we draw a Venn diagram, we have our two separate events, event A and event B, and this question wants us to find the probability of the overlapped area here. Okay, so, it's asking us to find the probability for B. Okay. So our equation, the probability of B as it depends on A, is equal to the overlapped area between them, the probability of that area, over the probability of event A itself. Okay. So let's go back to here and identify where all of the A events are, where one of the die is a 2. We did that similarly in the previous example. So we have this row here, and we have this row here. Okay. We also want to look at where the sum is less than 6. So for less than 6, I'm going to see here's a sum of 5, here's a sum of 4, sum of 3, and a sum of 2. So where do these intersect? Okay, where do both occurrences occur? Well, I see one of them being right here, and here, and here, and here, and here. They make like a letter T, 3, 4, 5, and 3, 4, 5. So there are 5 out of 36 occurrences for where they overlap. The probability of event A, we noticed that there were 6 spots in this direction, 6 in this direction, but one of them is shared. So instead of there being 12, there are 11 possibilities for event A. In our previous example, we recognized that these factors of 36, when they're identical and we invert and multiply to solve the division, results in basically the numerators over each other. Okay, so the probability of B, as it depends on A, would be 5 out of 11. If we look at this similar scenario, we're going to let the first die be a 2, this one we're doing one die that's 2. If we switch this slightly so that the first die is a 2, does that change things? Well, it does, because instead of having 11 possibilities now, you're only going to have the 2 in one direction. It just depends if I call this the first die up here or this the first die up here. It doesn't matter, I'm still going to have 6 options instead. So how does that change the calculations? Well, I'm not going to have as many overlaps, and I'm not going to have 11 out of 36 anymore. Instead, I'll clear this, and let's re-highlight the necessary portions to develop an understanding. Okay, so I'm just going to take a moment to put these back in again. There we go. And let's go back. So the first die is 2. Let's be specific. Let's say here's the first die, and here's where all of the first dies have a value of 2. Okay. The sum of 6, we have all the sums that are 5s, all that are 4s, all that are 3s, and the one option that's a 2. So, how many places do these two events intersect in? Well, right here, there are 3 of them. The 3, the 4, and the 5 in this direction. Okay, so we can say 3 out of 36 here. And under here, we can say that the probability of A, there were 6 possibilities out of 36. And when we do the division, we end up with 3 out of 6, which can be reduced down to 1 over 2. All right, let's do one final example that gets away from some dice and looks at another possibility. In example number 4 of your notes, it says a family is chosen at random from a set of all families with exactly 2 children. So if we have a set of all families that have exactly 2 children, find the probability that family has 2 boys if it's known that one of the 2 is a boy. All right, so again, let's draw this out visually first in a couple of different ways so that you can see it. One way I'd like to show this is if a family has exactly 2 children, and if we're sticking with just 2 genders for this particular question, we have possibility of boy-boy, boy-girl, girl-boy, and girl-girl. Those are the only 4 possibilities. Okay. Another way we can draw this out with event A, event B, and the overlap. The set of all families with exactly 2 children is this event right here. This is the overlap. Okay. The family has 2 boys. We can call that the second event. If it is known that one of the 2 children is a boy, we'll call that the first event. So if we were to place these into the Venn diagram, we know that boy-boy has to happen for both events. The only other scenarios where you can have one of them as a boy are these 2 right here. Boy-girl and girl-boy. So, what is the probability of the second event happening? Okay, so the probability of 2 boys with the first event happening that one of the 2 is a boy is equal to the overlapped region. I'm going to call it A intersected with B over the probability of the first event. So you can see that the probability where they intersect here is 1 out of a possible 4 altogether. I'll make that pink to show it as well. 1 out of 4 possibilities fits in the Venn diagram there. Okay. The other one where event A is also includes the girls out here as a separate event. Okay, so there are still 4, but that first event has 3 out of the total 4. Because remember, probability in the denominator is the no restrictions clause. Okay, so altogether within that circle, there are 3. Right there, out of the total 4. We realize that comes out to 1 out of 3. Let's adjust this ever so slightly. So now the family has 2 boys. We'll keep that as the second event. And they know that the first child has to be a boy. So not that one of them is a boy, but that the first one is a boy. How will that change things? Okay. Well, out of all these possibilities, the first one is a boy, can be BG or BB. But BB can be in the overlap region because it also meets the criteria of the second event as well. That means that the events where the girl is first are outside the set. Girl-boy and girl-girl. So, what is the probability then of having 2 boys where the first child is a boy? So the probability where they overlap is still 1 out of a possible 4, 1 out of no restrictions. Down here, though, the number that are inside the first event has been reduced down to 2 out of 4. And so that will change the probability to being 1 out of 2. Okay, I encourage you to use Venn diagrams to help sift and sort between these 3 variables. Which 2 are you given? Which one are you trying to find? That'll help you know which version of the equation you can go straight to, or you can always use this one and just rearrange it, or this one and rearrange it. And if you have any questions, please let me know. Thank you.